All right, y'all. So what I'm going to be doing today is going over electron configuration, and hopefully this will help kind of make the notes make a bit more sense. So if we start out looking at atomic structure, what we've looked at before are the Bohr models. And when we look at the Bohr models, we see a couple things. We have our nucleus in the center with our positive protons, our neutrons, and then we have our electrons, which I should probably fix this down now because I'm going to draw a lot of rings. All right. So here's my Bohr model, and I'll go ahead and throw some 1, 2, 3, 4, 5. Basically 5 protons, 5 neutrons, 5 electrons. So when we look at a Bohr model, you'll notice a couple things. One, the electrons are around the nucleus. Electrons around nucleus. And there are also distinct energy levels. Distinct energy levels. Basically levels where the electrons reside. So right down here we have n equals 1, or the first energy level. And then right here we have n equals 2, which is the second energy level. So a big part of this is that the electrons all fall within boundaries that we call orbitals. So that's kind of the key word here, orbitals. Now, orbitals don't necessarily say electrons will always be here, but the one key thing about orbitals is this is most likely where electrons are found. Because electrons move around, so they're not always in one place, but most of the time they're going to fall within their orbitals. In addition, each orbital can only hold 2 electrons per orbital. And orbitals exist in these different energy levels. So they exist within the different energy levels. So before I take orbitals further, I'm going to take a brief aside to look at energy levels. And you'll notice that before I represented it with n. And the thing about energy levels is we have 7 of them. 1, n equals 2, all the way to n equals 7. And something to note about that is these coincide. I don't know if that's how I spell coincide, but coincide with the 7 periods, or also rows, of the periodic table. So when you're looking at the periodic table, you can generally know what energy level an atom has, up to, if you just look at the period in it. So an element in period 5 will have the 5, n equals 5 as their largest energy level. So that was my brief aside, and we're going to go back into orbitals now, because these orbitals, once again, are in the energy level. So we're going to go back to orbitals. And there are also 4 types. We have the S, P, D, and F orbitals. Each one has a different shape. S is spherical. P has kind of like a figure 8 shape, but there's 3 of them per energy level instead of 1 like the S. So they kind of make this weird shape where you have something on the x-axis, the y-axis, and the z-axis. So we've got 1 on each axis if you're looking kind of like in 3 dimensions. D orbitals are kind of clover shaped, but I can't draw it, so I don't expect you to remember that. And F orbitals are really complex. And again, I definitely can't draw it, so don't worry about the shapes for D or F, just kind of S and P. So one thing I generally like to look at before we start going further into this is the periodic table. It's going to be our #1 tool moving forward. So if we look at the periodic table, we can kind of reclassify it. First off, when we're talking about orbitals, helium is normally over here, but we're going to drag that bad boy right over there. So I'm just going to kind of do a little cut and pasting. And then let me just reconnect that. All right, we put helium where it's supposed to be, right there. Because helium has s orbitals only, and because of that, we can kind of just classify this whole section as the s orbital area. And this will make a little more sense in a second here. Over here on this side of the periodic table, this is the p orbital section. This is the p orbital. Right here, down in this transition metal section. Oh, oops. In our transition metals, this is the d orbital section. And last but not least, we kind of have this lone zone down here, the lanthanides and actinides. And that is our f orbital section. So I'm going to refer back to this diagram a lot. So right now, I just want to put it in your minds, and then we're going to come back to it. So there's been a lot of information so far, so I'm going to try and now kind of recondense it and bring all this info together. So with that, let's start with the s orbitals. S orbital. The s orbital appears in each energy level. What I mean by that is that there is a 1s, a 2s, a 3s, a 4s, a 5s, 6s, and a 7s orbital. All of these exist. The number in front, I guess I should use green to keep consistency. This number in front tells us the energy level. And then this number right here tells us the orbital. Now, that's the s orbital. We're going to now move on to the p orbital. I think I did p in red, so p orbital appears from n equals 2 onwards. So there's no 1p, but there's a 2p, 3p, 4p, 5p, 6p, 7p orbital. So once again, that number in the front is going to be the energy levels, kind of changing the way I'm notating this. Those are going to be our energy level. And then this guy in the back is going to be the orbital. All right. Again, with the d orbital, it's actually going to follow kind of the same trend we just had. D orbitals appears from n equals 3. And again, that's going to be onward. 3 onwards. However, we only have 3D, 4D, 5D, and 6D. We don't have anything that yet accesses the 7th D. That will kind of make sense in a moment when I start showing you the periodic table again with this. But once again, the front number is the energy level, and the back letter is the orbital. Lastly, we have our f orbital, which appears, you guessed it, from n equals 4. And we only have 4f and 5f. You might notice that for p orbital, we have all the way to 7, d orbital only to 6, f orbital all the way to 5, and again, p orbital 2, 3, 4. So they're kind of meeting in the middle. So with that said, let's kind of look at how this makes sense with some of the things like Bohr model, etc. So I want to look at the Bohr model first. So we're going to come back to our Bohr model. And something you may remember is when we look at the rings, each one has a certain capacity for electrons. So as we move out, but now we can look at these in terms of energy levels. This is n equals 1, n equals 2, n equals 3, and actually I'll go ahead and throw a 4th one there, even though it's really sloppy. I'll redo that one. And then n equals 4. So if we look at that, you might remember that in the Bohr model, the first ring can only hold 2 electrons. The second ring can hold 8 electrons. The third ring can hold 18 electrons. And the fourth ring can hold 32 electrons. And this actually is the same all the way to the 7th, which also holds 32 electrons. So the question is, where did those even come from? Well, we're actually going to come back up to our orbitals first. So we're going to add to this. There's only one s orbital per energy level. And now that orbital, again, if we think about the shapes, is a sphere. And because there's one s orbital per energy level, and orbitals each only hold 2 electrons per orbital, that's a really important point. Then n equals 1. Again, the only orbital in the first energy level, 1, is s. That would therefore mean that there can only be 2 electrons because there's only one orbital, the s1. Now, p orbitals come in threes. There are 3 p orbitals per energy level, and each orbital holds 2 electrons. Therefore, in the second energy level, we have the 2s and the 2p. So that's 1s and 3 p's, making a total of 4 orbitals. There are 4 orbitals. We have an s, a p, a p, a p, and 4 times 2, 2 orbitals for each electron, or 2 electrons for each orbital, is 8. N equals 3. When we go to n equals 3, we have an s orbital, a p orbital, and d orbital. And d orbitals. So we have s, p, and d orbitals. D orbitals, however, have 5 d orbitals per energy level. I'm going to separate that d a little bit because it looks like 5 orbitals. So now when we get to n equals 3, we have 9 orbitals. We have the s, the p, the p, the p, the d, the d, the d, d, and d. And again, that's going to be 18. Now all you need to know is f is 7 orbitals per energy level. And so now 7 times the 2 is going to be 14. 14 plus the 18 from the ones before is going to be 32. So that's going to be a total of 16 orbitals. And that's going to continue down here where we also have 16 orbitals. All right, so that's all that stuff out of the way. So now the big question, how the heck do we even read any of this? Well, we're going to come back to our periodic table. And for the sake of this periodic table, I'm actually going to redraw that because I want to remove helium and put it on the left side. So I'm just going to go ahead and kind of do my best to draw this. Yeah, let's see. I'm not going to draw the whole thing, just kind of these top ones. So if we remember, we have our S kind of taken up this side, our P taken up this side, our D taking up the interior, and we're not really going to worry about F. So where do these configurations 1s2, 2s2, etc. come from? Well, let's just first label these 1, 2, 3 for the rows or the energy levels, and let's start with hydrogen. Hydrogen is right here. It is in the first energy level. It only has S, so it's S, and in the first row, so it's going to be 1s. And I like to think of these as positions. This is position 1, this is position 2, this is position 1, this is position 2. But it can also represent the electrons that are physically in the atom. And hydrogen only has 1, so this is 1s1. So I'll write that in here. If we move on, we have helium right here. Again, first energy level, only the S, and it has 2 electrons, or it's in the second position. You can read it like that too, so it's 1s2. When we move down to these lower elements, so now we're going to go to lithium and beryllium. Lithium, you might just say, oh, well, it's in the second row, and you'd be right. Row 2, it's only got S, and it's in the first position, or only has 1 2s electron. This is specifically referring to the second energy level, the s orbital, the first electron that lithium has. However, if we look at the number of electrons, which also can just be represented by these little exponents, they need to equal the number of electrons in the atom. Hydrogen has 1 electron, 1. Helium has 2 electrons, 2. Great. Lithium has 3 electrons. Yet we're only representing 1 right here. So we need to remedy that. And the way this works is with electron configuration, you actually write everything that came before. So before lithium right here, we actually have helium because we read backwards. And so helium is going to come first. So we have 1s2, 2s1, and that is lithium's electron configuration. What this directly means is that if we look at the lithium atom, it has the first energy level all the way at the bottom, and it has 2 electrons in it. Then it has a second energy level, and it only has an s orbital there with 1 electron in it. Beryllium is going to follow the same path, and that's going to be 1s2 to kind of make up for that helium, and then 2s2 because it's at second position, and we see a total of 4 electrons, which is correct. So what happens when we move over? So now we're going to kind of move our way over here, and let's go ahead and fill in carbon. Carbon is now in the second row. We are in the p orbitals, and you can kind of look at it as position 1. I'll change the color on that so we can see it now. Position 1, position 2. So 2p2. But once again, we have to have everything before it. So we're going to write 2s2 and 1s2. Now we're only writing the full orbitals ahead of it. We don't write 1s1, 1s2, 2s1, 2s2. We're only writing the full orbitals because that 2 right here makes up for the 2s1, and this 2 makes up for the 1s1. So if we total it up, we now have 6 electrons, which is accurate. So hopefully this helps. I will post much more videos. A couple things to be wary of is because the d orbitals start at 3d, when you come to this 4th row right here, you have your 4s, 4s, then you start 3d all the way down. 4d doesn't start till the 5th row, where we have 5s, 5s. And I like to do electron configurations like I'm reading a book, left to right, up and top to bottom. And so just a quick configuration of something there at the bottom. I'll do titanium, which is the second one. And I'm going to do it really fast, and you can try and work it out on your own time. It's 1s2, that covers this first part, 2s2. So I'm just going to highlight what I'm covering. 2s2 will cover that. 2p6 will cover this whole section. 3s2 will cover this section. 3p6 will cover this next section. 4s2 is going to cover the 4th s orbitals. And finally, it's going to be 3d2 because it's a second position within the d orbitals, the 3d orbitals. So I hope this helped. If you have any questions, always feel free to message me.